Okay, so today we're going to derive the general T.dS relations. So basically the only thing we need to do is to recall the second principle of thermodynamics, equation, which is what? T.dS minus the work equal to the change in energy. Okay? So in this equation, the E over here is equal to the change in internal energy plus the change in kinetic energy plus the change in potential energy. Okay, so all right, so really the only thing we need to do over here is that to remember that the expression for work done by pressure is equal to what? Will be P dV. If you remember, we had the expression work equal to the integral, and that's why I said this notation is really more correct. So if we substitute this expression here over here, we're going to get so that this equation here, we can rewrite it as T.dS minus P dV is equal to dE. Okay? Now, if we say that if we neglect kinetic and potential energy, basically what does that imply? Is that the change in internal energy would just be left, the change in all energy would just be left with the term of internal energy. You'll have T.dS minus P dV is equal to du. And this is really what is known as the first T.dS relation. Okay, so remember that if we deal with U, this would be equivalent to CVs, so this works more for closed system. Okay, but we can actually rewrite the same equation here in function of the enthalpy. So here we say recalling the enthalpy equation, which is what? Enthalpy is equal to internal energy plus the work done by the pressure. Okay, so here we have the differential form. So we take the derivative of this, what do we have? And this is du plus what? This is like having a function u, so this is the derivative, this would be equal to what? U prime v plus u v prime, no? So here we kind of do the same thing. This would be du plus what? P dv plus v dp. This would be the total derivative. So here we can just rewrite that du will be equal to what? dH minus pdv minus vdp. So now we substitute this one into here. So substituting this Roman 1 into equation A, this should give us the second T.dS relation, T.dS minus P.dV equal to what? dH minus P.dV minus VdP. So over here you can see that this term will cancel this one, so that at the end we have an expression that looks like T.dS equal to dH minus VdP. So these two expressions are really the general T.dS relation that I'm just going to summarize on the next page. So let's see. Our equation A is what? T.dS A T.dS minus P.dV was equal to du. So this one we can just rewrite it as T.dS equal to du plus P.dV. And the second one is T.dS equal to dH minus VdP. So this one is already on the correct form. So basically the two general T.dS relations will be what? So we have T.dS equal to du plus P.dV, or T.dS equal to dH minus VdP. Okay, but in the book, most of the time, you know that we use the specific values. So you can just rewrite it, or using specific values, which means per unit mass. So basically, which one would it be? Would it be this for the volume, and this for the enthalpy and the internal energy? And I think that should do it. We get what? T, so this is uppercase S, this will be T lowercase s will be equal to D lowercase u plus P lowercase v. T.dS will be equal to dH minus V dP. So this will be our general T.dS relations and T.dS relations. Okay, so that will be it for this video.